So in the previous video, we talked about the orientation of joints relative to principal stresses. So we can understand this better looking at a Mohr circle. This is I'm just going to draw a pretty typical situation. We've got some layer of sedimentary rocks, we've got some sandstone, some other sedimentary rock. We'll do a limestone here. And during the burial of these sediments and get down deep enough, they turn into rock. The weight of the overlying sediments will often lead to the vertical stress being sigma 1, so the strongest stress coming from above due to the overlying sediments. And we will often find that veins form with this sort of orientation. They're parallel to sigma 1, and as we said previously, perpendicular to sigma 3. I'm trying to make them a little kind of pointy on the ends. That is something that we observe. So the question is, if you take a look at the Mohr circle and think back to those lectures, can you explain this orientation using the Mohr circle? So go ahead and pause the video and think about this a little bit. Try to connect this to what you saw previously. Before, we had this fracture envelope. And we talked about how the point where the fracture envelope touches the Mohr circle, we can define that as an angle 2 theta. And that theta, in terms of real space of like sigma 1 coming down, so this would be a 2 theta tip of this is about a 120 or so. So this would be theta around 60. And we define theta as the normal, the angle between sigma 1 here and the normal to the plane that we're talking about. Okay, so this is theta around 60 degrees. So that's not what we're describing here. We're looking at sigma 1 is parallel to the orientation of the crack. So pause the video again and see if you where on the Mohr circle, if you were to draw another Mohr circle, where in the Mohr circle would this orientation be, where sigma 1 is parallel to the long direction of those planes? Okay, so the answer is, so if we basically just tilt this another 30 degrees, that would be theta equals 60 plus 30 would mean theta is 90, 2 theta is 180, so it's right here. 2 theta all the way over here. So it turns out that that when the fracture envelope goes into negative normal stress, it comes around like that, okay? And so this would be negative normal stress. So that's like pulling things apart. So if you have a Mohr circle can touch at 2 theta equals 180. And that is how we understand. So let's just illustrate that, or just notate it. It's Mohr circle. Fracturing. I put it in quotes because it's not the Mohr circle fracturing, but it's indicating fracturing at 2 theta equals to 180. Okay, and that's what we see in these sedimentary basins. So this is what we call the type of fracture that forms in this sort of situation is a tensile fracture. So it makes room, it opens space. In the situation, another way to look at it is basically the space is going to open in the direction, it's going to open parallel to sigma 3. So it opens parallel to sigma 3. And I always find it's a little confusing when you say opening. So if we zoom in on one of these things, kind of exaggerate it like that, it opens up like that. We could think of it like that. And so that the way that it opens is in the same orientation as the least principal stress. So that sort of makes sense. If we're pushing on a box, from all directions, and we're gonna make some space, it's gonna be the parallel to the direction that we're applying the least stress. And in this case, if we actually go into negative, it means sigma 3 negative, it means we're actually pulling this thing apart. However, we generally don't think of rocks being actually under real tension. They're not actually being pulled apart. These things can happen deep in the crust. So another question: how could we open a tensile fracture deep? So there's so much pressure deep in the crust. And the answer is fluid pressure. Okay, so it's not that rocks are actually experiencing being pulled apart like we could do in an experiment. It's fluid pressure sort of can, imagine pumping this. If there's a fluid in here, pumping it up, it's going to act opposite of sigma 3. So we'll call fluid pressure P with little f. Fluid pressure pushes against normal stress. So imagine a an interface between two grains, and that interface is experiencing some normal stress, might also be experiencing some shear stress. And in there is a fluid. If we could kind of zoom in on that, we think of the fluid as pushing away on the, I'm just going to draw my little box around this like I showed. So we've got the fluid in here. It's pushing against the walls. And so we refer to what we call effective normal stress. And effective normal stress equals the normal stress minus the fluid pressure. And materials behave according to effective normal stress, not applied stress. So in a Mohr space, what that means is that we may have, if we're just plotting like a normal Mohr circle, we're over here, we're not in the tension field. So this would be sigma 1, sigma 3. But really the thing that's going to control when they fracture is not normal stress, it's effective normal stress. So when we add the fluid pressure in there, the Mohr circle will move over. And we have here effective principal stress, an effective sigma 3 as well. So we've taken the normal stress we had and subtracted the fluid pressure would have, the magnitude of the fluid pressure would be determined by how far over the Mohr circle moved. And so what can happen then, if we just kind of zoom out, we may not be at failure. Here's the fracture envelope. But if we add enough fluid pressure, the Mohr circle will move over. It doesn't change its diameter, it just moves over, and then it will intersect, it will hit the fracture envelope and break. And depending on the size of the Mohr circle, this one might actually hit up here and make a shear fracture. But if it was a smaller, let's say it was a smaller circle, it's going to come right over here and hit at 2 theta equals 180 degrees. So we distinguish between bigger Mohr circles that are going to hit, in this area. Those are going to make This is sigma 1. Those are going to be, have this kind of orientation. They're going to be the kind that where there's sliding, there's shearing along them. Those would be the x's. And for this other one, it's going to open up in this direction. And those aren't going to, the motion there is sort of an opening motion. That would be in this area here.